screen. Let me know if you guys can see my screen right now. And if at any point I'm going too fast, just put in the chat and I'll like slow down. And if you have any questions, I'll answer them, of course. So yeah, can you guys see my screen right now and hear me? Yeah. Okay, cool. So we'll just carry on and start now. So firstly, I just wanted to go through these kind of general mechanism rules and definitions just one more time quickly. This is probably something that I would just advise you guys just screenshot and potentially just making flashcards on Quizlet or Anki or something like that. Just because like people getting confused on when to use which mechanism, but I feel like if you understand these definitions, then you'll be able to identify which mechanism the question we're talking about, especially the more complex mechanism questions that come up and that we'll go through later. So I'll just leave this on the screen for a couple more seconds, maybe if you guys to screenshot, but the slides will be in the group chat as well. And then we'll just carry on. So yeah. Okay, I'll just move on now. Someone asked me also to go for like the kind of MyUCAT naming priority, so the order of what takes priority over what. This is kind of the general order. Again, probably just screenshot this. And I think that with like the nomenclature and naming the different organic compounds, it just comes with practice. So just find those exam questions, just draw out your own compounds, practice naming them. I think that's how you can get good at naming the compounds. So yeah, this is kind of the general order that I found. And triple bond isn't really covered in A-level, but it was mentioned, so I just thought I'd put it in there anyway, just in case they throw that in there. Leave it on the screen for 2 more seconds, then we'll just keep going. Yeah, okay, I'll just move on now. So I think yesterday, this was kind of a general misconception, so I just wanted to cover this again, and it's kind of the importance of pi bonds and sigma bonds, and this is something that's covered in OCR and not AQA, but I still feel like it's quite useful to understand how this works. So we'll just go through it now. So the carbon-carbon double bond consists of an overlap of electrons in the 2s subshell to form a sigma bond, and that's kind of just one single bond, as you can see in the image on the right. That's formed between the two carbon atoms within the double bond. And when this is formed, the carbon atoms only use 3 of their electron pairs to form this sigma bond. So there's always one spare p orbital that has one extra electron. And when these p orbitals overlap, that's what forms the pi bond. And the 2 orbitals that form the pi bond lie above and below the plane, as you can see in the image on the right. And that's to maximize bond overlap. And as a result, the pi bond is almost exposed and has a high electron density, which means that there's lots of electrons contained within this area. And that's why electrolytic addition can occur, because this electron density attracts electrophiles, and that's why it occurs. So I think that was I think I didn't explain it very well yesterday, but I think hopefully this makes more sense to you with the diagram. If you guys have any questions about this, then feel free to put them in the chat, but I can't see any at the moment. We'll just wait a sec. Does that make sense to you guys? Just put like a yes or no in the chat so I know that I explained it well. Yeah, that makes sense. Cool. Someone said, how do you count the number of pi and sigma bonds? I'm not sure if that's something that you would be required to do at A-level, but I think that dependent on so for example, in the diagram on the right, you can see that for every carbon double bond, there's always going to be 1 sigma bond, and there'll be 2 pi bonds for every double bond. So I think, yeah, that is apparently the question about that in OCR. I did do AQA from A-level, so I'm not 100% sure how you do that, but I can find out and put in the chat and figure out for how you guys do that. What are the green orbitals, please? Those are just the s orbitals, I think. So yeah, but I'll find out how to calculate the number of pi bonds and sigma bonds more accurately and put in the chat later. But I think that's all for this, so we'll just move on. And yeah, we'll do exam questions later, of course. So I just wanted to also go through, someone asked me to go through kind of like some practical skills for organic chemistry. So I just went through reflux as one of those. So in reflux, we essentially are heating the reaction mixture for a really long period of time, and it's heated to boiling point. And the vapor is formed, which escapes from a liquid mixer, so it's liquid mixture through the condenser, and gets changed back into a liquid, so it's condensed, and then gets returned back to the bottom of the round bottom flask. And when heating during reflux, you aim to keep all of the chemicals inside the reaction vessel. And And yes, there have been questions before that ask you about drawing the apparatus. So it's just something that I'd make sure to draw, and especially make note of the direction of where water goes in and water goes out, because sometimes in some questions they'll give you an apparatus that's drawn wrong. So they'll have water going out and water going in at the wrong points. And it will ask you name two errors with this diagram, the way the student has set up their apparatus. So yeah. And examples of reactions where heating under reflux can be used is the formation of carboxylic acid from primary alcohol using potassium dichromate. And if you were to use distillation, that would form the aldehyde. But by using reflux, it means that the reaction keeps going, it goes to completion and it forms a carboxylic acid. And another example is the production of an ester from an alcohol and acid in the presence of an acid catalyst. And also you need to also understand the function of, and yeah, you need to be able to draw the distillation too, and also the Buchner funnel, which we'll go through in a second as well. But just to carry on, so you also need to know the purpose of the apparatus. So for example, the condenser prevents organic vapors from escaping from the reaction vessel as it's open, so by condensing into liquid, which I think is quite obvious, I think. And this is just a kind of safety point, is that the end of the condenser must never be sealed, as the buildup of gas pressure could cause the apparatus to explode, which would cause damage, obviously. And sometimes in the round bottom flask, there would be anti-bumping granules added to prevent kind of rigorous and uneven bubbles forming by making small ones rather than really large ones. So it allows quite even boiling. So this is something as well to remember, as I think this is quite like a fan favorite for examiners. And how do you remember which one is with a closed at the top and which one is open? So reflux will always be closed at the top. I mean, open at the top. It will never be closed at the top, sorry. Do you guys have any questions about this? I think this is quite a good practical. I'll just wait for a sec and then we'll move on. I think, does that make sense? Just put a yes in the chat again, if this makes sense. Someone said, so anti-bumping granules allows for minimal bubbling. Yeah, it just makes them bubble smaller as opposed to really big. Would you have to draw a thermometer on this? No, you don't have to draw a thermometer on this. And if you drew this, yes, you will get full marks because this was taken from a practice paper. You could draw a thermometer, but I don't think you need to. And are those the only reactions that use reflux? Yeah, as for A level, I think those are the only ones that you need to know, or the most commonly assessed ones in A level. Do you seal with distillation apparatus? I think you do need to seal with distillation apparatus because it kind of like comes up and then the condenser comes down the side and then collects in an ice bottle. How do you know which way around the water is? I'd say just practice drawing it and just kind of memorize it. That's where it goes out. But I feel like it kind of makes sense because you need the water to kind of go up with the liquid to condense it. So that makes quite sense. Yeah, and the marking point is always to prevent large bubbles forming. So just memorize that. It comes up quite a lot. Any more questions? I think that questions in the past typically haven't really asked exactly why the water goes through the bottom, but it's just to ensure that as Preet said, it goes against gravity, which is the direction that the vapor is going to go up, so it condenses it. But typically the question would be more likely to kind of swap around the water in and water out and ask why, and ask for why that's wrong. But yeah, the answers in the question, the answers in the chat are correct as well. So well done, guys. I'm going to move on now. I think that makes sense. This is also another practical, the recrystallization impurity practical, and this is kind of a exam favorite. I think it comes up almost every year in either paper 3 or paper 2. So for the method, you would just firstly dissolve the impure crystals in the minimum amount of hot solvent, and then filter the hot solution through a hot fluted filter paper. Then let the solution cool in ice and recrystallize, and then filter them by suction filtration using a Buchner funnel under reduced pressure. And then you want to dry the crystals between 2 sheets of filter paper and then wash and dry them with cold water. And it's really important for this. And yeah, this is used to purify aspirin in that practical. But it's just this particular part about recrystallization impurity that comes up quite a lot. And they can do this in a context that's not aspirin, so they can give you kind of a novel and never seen before context. So it's really important for this to know like why each step is performed, and that's kind of what practical questions at A-level test you on. It's not actually the method itself. This is an AQA, Chloe. Sorry. And so it's not necessarily the method itself, it's knowing why you're doing each step and why each step is important. That's most commonly assessed. And fluted filter paper is just type of filter paper. I think it's just thicker and it's like not gonna kind of like burn within heat. So I feel like in A level, the filter paper that you would normally use, for example, in normal standard filtration, it would kind of set on fire if it was heated or like melt or something. And yeah, it is an AQA. So we're going to start. So why the minimum amount of hot solvent is used? And this is to obtain a saturated solution, and it dissolves both the compound that we want and also its impurities. Again, this is just something to memorize. I just say just make it into a flashcard and just memorize it because it does come up quite a lot, especially in paper 3 for AQA. So it needs to be filtered using hot fluted filter paper, and that's just to remove any insoluble impurities, so things that aren't soluble in water. And you use heat to prevent the crystals reforming during filtration. We don't want them to. Crystals are formed during cooling, so we just add heat to stop them forming too early. Essentially, that's the purpose of that. And then they're cooling ice, as I just mentioned, the crystals are formed during cooling, so it increases the yield and makes sure that more crystals can be formed in a given period of time as ice is cold naturally. And then they're washed with cold water to remove soluble impurities. So things that are soluble in water, so they'll like wash off with the water. Does anybody have any questions about this? Yeah, okay. A saturated solution is just one that it just contains everything that's within the solution. So as it mentions, it dissolves the compound and its impurities. And I think a standard solution counts as in titrations counts as a saturated solution too. Yeah. I'll just move on because I can't really see anything else. I don't want to overrun again. So again, there's more questions that they can typically ask you. So for example, one question might ask, why is suction filtration? So why do we use the Buckner funnel? And it just reduces the pressure and makes filtration faster. And it makes sure that air passes through the sample and not just around it. And a Buckner funnel is more used than a gravity funnel, which is what you would use during normal filtration because it's quicker and the sample produced is drier. And the yield might be greater than expected because they aren't dried properly. And the yield might be lower than expected because crystals are lost during the process of filtration and washing, and because the product stays in the solution after recrystallization, and also because other side reactions occur. And then this diagram on the right, I would advise that you would learn how to draw this, as this comes up sometimes as a little 2 marker. And sometimes examiners would expect you to draw it. When you draw it, make sure that you include that is going to the vacuum pump, and just make sure that you label it. Again, just practice this. I think I just made these into posters, these diagrams, and just put them in my room and just looked at them and practiced drawing them over and over again until they went in my head. What does it mean? What does it mean by product stays in? Yes, you are expected to draw it vaguely. What does it mean by product stays in solution after recrystallization? Oh, so it means that so essentially when you are after you've recrystallized them, so when they're cooled in ice, and once you filter them, it kind of just stays within the Buckner funnel, and it's not doesn't actually get filtered down, so it will still remain within the filter paper. If that makes sense. I mean, sorry, it would go down into the Buckner flask. It would be filtered, and the crystal is supposed to like be insoluble and stay on top of the filter paper, but it goes down and is lost at that point. So it's still, the crystals are still part of the filtrate. That makes sense. I kind of messed up a little bit, but hopefully that makes sense. Yeah, you are expected to draw this. Any more questions about this? Do we need to know anything about the vacuum and this? Yeah, you just need to know that it just makes it faster and allows filtration to occur under reduced pressure and ensures that air passes around the sample, not just through it, as it says here on the slide. I think that's the main thing that exam questions assess. And these are typically worth quite a lot of marks, like sometimes come up as 6 markers or maybe 5 markers, just to understand why these processes are occurring. But does that make sense to you guys? But yeah, again, just to check in to make sure that everyone is on board. And is the pace all right for you guys as well? Just let me know if I'm going too fast or anything like that. Cool. Okay, we'll keep going. Okay, so another thing that sometimes comes up as well is kind of determining melting point of apparatus. So the method for that is just to place the sample in a capillary tube, and then you place the tube into a kind of melting point apparatus and you heat it slowly. That shouldn't say head, it should say heat. Sorry about that. And you just record the temperature when the solid starts to melt, and then the temperature when it has melted completely. And then typically questions ask if there's an impurity or if it's pure, how does that affect the melting point? So if there are impurities, it will melt over a wider range. So for example, say if the temperature, the melting point of the substance was 105 degrees Celsius, which I think is the melting point for aspirin. Stephanie, I'll go back in a second. So in what I've already say, for example, the melting point was 105 degrees Celsius, it would melt in the range of, for example, 101 to 110 degrees Celsius. Or the melting point, or slash and the melting point will be lower than the true melting point. So rather than 105, it might melt at 92 degrees Celsius due to the impurities within the molecule, within the compound, sorry. Whereas if it's pure, it has a very sharp melting point, so it would melt at specifically 105 degrees Celsius, and that melting point value that you obtain experimentally would match the data source value. And I did see some question that asked why a pure substance might melt at a temperature that's different from the melting temperature. And that would just be because the temperature on the thermometer is not the same as that of the sample. So it's just a slight inaccuracy with that. And yes, the yield is determined referring to crystals, and the yield would be greater because the excess water would add mass to the crystals. So when you calculated your percentage purity, it would be higher because it would look like you had formed more product than you had. And yeah, it does. Aspirin does make needle-like crystals that when pure, and they're kind of like shiny and white. But I think your school will probably have done that practical, and you see them. And then on the right, that's just the apparatus, the multi-point apparatus that's used to determine the melting point. And then there's just some properties. For example, the heating oil has to have a higher boiling point than the sample's melting point, and it has to have a low flammability. So that could be an exam question. It could be like name two properties of the heating oil used when calculating melting point. But yeah, I think this is quite a good question that comes up that when it comes up because it's something that you can just memorize. And yeah, pure aspirin is quite shiny and white, and it's quite almost quite reflective, and it's very like as Aisha said, it's quite needle-like and very like fine. Um, and yeah, I think it is called a field tube as well. Yeah, as Madeline said, the water will add weight, add mass when you weigh it. But yeah, does this make sense to everyone? Hopefully it does. Volatile means like its tendency to be a liquid, I think. So if this I think HS might be AQA. This was covered in AQA, but it might be relevant for OCR, but I'm not 100% sure. But I'm assuming it is because I think there's quite a lot of overlap. And yeah, you might as well memorize the apparatus. It doesn't come up very commonly. More the theory behind it about whether how the melting point is affected by impurities slash purities, but still they could do this. And sorry, I meant to say turn into a gas. I was thinking about viscosity. Sorry, sorry, Pavisha. So on the line it says the temperature on the thermometer is not the same as the sample. It essentially means that there's kind of like a slight inaccuracy. Um, sorry, this means there's a slight inaccuracy. So the thermometer sometimes might just be slightly inaccurate, and the sample might just be a different temperature to what the thermometer is actually showing, and that might just be due to like a calibration error or human error. And for AQA, I have seen a past paper question that asks what aspirin looks like. So that's why I just thought I'd mention that for you guys. I think it was a 2 marker. Um, but yeah, hopefully that makes sense to you guys. Any more questions? Uh, if you guys are ready to move on, just put yeah, yes, I'm ready to move on in the chat or something so I know you guys are ready. But I can't see any more questions, so I'll just move on now. Cool. Okay, this is just I found this online, just kind of like an organic synthesis kind of route map. I just screenshot this and just practice drawing this over and over again. So yeah, this I don't really know how to explain this. It's just kind of just there. But yeah, this is quite good, I think, to learn. And this is for OCR, but all the mechanisms are basically the same for OCR and AQA, so you could still use this interchangeably if you do AQA. And I think in A level, I just got a piece of A3 paper and just started from an alkane and just saw how many I could do and just practice writing that out over and over again. But yeah, I'll leave this on the screen for a couple more seconds in case you guys want to screenshot it or anything like that. But yeah. Yeah, don't worry, Zara. Coming up next is the aromatic one. Here you go. So you guys can probably screenshot this. This is basically the same for AQA. I think there's just a few extra added ones on this that we don't really do, but still relevant. Are we able to ask our paper and stretch out in the exam? Yes, for sure. And in my mechanisms, I remember doing it in pencil first and then going over it in pen, just to make sure that I drew everything correctly. And yeah, I'll go back in a second now. And yeah, as Masood said, blurting this out helps, and that's how I memorize it. Nafisa, that's how I memorize it. But I'll go back now quickly. Did you say aromatic for AQA? I'm not sure what you mean by that, but aromatic and arene are the same thing, and these are all aromatic molecules or aromatic reactions involving aromatic compounds. But I'll just go back now for H. Um, do you know why you add HCl/H2O when turning a nitrile? Oh yeah. I mean aromatic synthesis? Do I need to know it? With regards to aromatic synthesis, the main thing that you need to know is electrolyte substitutions. That'll be nitration and then also Friedel-Crafts acylation, which I went through yesterday. So if you just watch the recording from that, um, sorry, just to clarify, do we have to draw all our diagrams using black pen only? Yes. If you use blue pen, it won't be scanned by the computer. But I think they've now got better scanners that can detect pencil. But um I would just use black pen just to be safe. It's better to be safe than sorry, I think. Do you know why you add HCl/H2O when turning a nitrile into a carboxylic acid? It's never made sense to me. I think you need to add HCl because we're probably going to make ammonia or ammonium chloride as the product. And I don't think this is covered in AQA. You're probably going to make ammonia or ammonium chloride, and you probably need hydrogens to be supplied to produce that as a product and allow the reaction to go to completion. So for math, should we draw graphs in pen 2 due to the scanner? And yeah, for AQA, the Chemorise one is good too. So for math, should we draw graphs in pen 2 due to the scanner? Yeah, just draw in pencil first, then go over it in pen. That's what I did. But I think yeah, as Hassan said, I think H3 pencils are good too. But don't worry, say if you did do it in blue pen and it wasn't detected by the scanner, they would just mark it by hand and then input your marks online. So don't worry, guys. Your exam will still be marked, like it's not that deep. And I'll just go back to this one now again. It shows how to synthesize. So with Molly, with that one, I think it has come up before, but it's really, really rare. And typically they would use the acyl chloride example more. Do you know the mechanism from nitrile to amine? No, I don't think you know the mechanism. You just need to know the conditions and the reagents that are used. Probably should have put the AQA one in, but I'll send it to group chat after as well. So don't worry. Okay, is everyone ready? I'll move on for this now. Move on from this now because yeah, went up too long. And this is just one more aromatic reaction pathway. With regarding phenol, so just a benzene with an OH group one. And with the synthesis map, I think there's not really a way to like kind of like memorize acronyms. I feel like you just either know it or you don't. So I just keep writing out over and over again, just keep practicing. And I feel like the more exam questions you do, the better you'll get at memorizing when to use what mechanism is talking about. So just keep practicing, guys. Don't worry. It will all click eventually. So don't worry. Sure. Okay, is everyone ready to move on now? I feel like it's been on quite a while now. Sure. So now we're going to go through some exam questions. And these exam questions that I chosen are from OCR, but I thought that they were like really good questions. So I just stole them from OCR because they're quite challenging ones. So we'll go through these and so even if you AQA or LECR, the questions are still really relevant because it's kind of like more application of your mechanism ability as opposed to actually knowing the mechanisms. So we'll just go through these now and we'll get started. So I'll just walk you through kind of like my approach to how I'd approach these organic synthesis questions with kind of like unfamiliar or kind of random molecules that you might not have encountered before. But yeah, we'll get started now. So it says lactic acid is a naturally occurring chemical which can be synthesized from ethanol, CH3CHO, as shown in the steps below. So we've got ethanol, and we can see they've added HCN to form compound E, and that's kind of an intermediate. And then we have step 2, where they're converting compound E into lactic acid. So it's a carboxylic acid with an OH group on. So when I'm answering this question, I'm going to highlight the information they give me. So it's called lactic acid. I've probably heard of it in biology, but it's not really that relevant. So probably just ignore the fact it's talking about lactic acid. And we know that it's being synthesized from ethanol, and they've shown us the picture of that. So when drawing compound E, what mechanism do you guys think that this question is talking about for step 1 in particular to form compound E? If you guys could just put in the chat. I'll give you guys a couple seconds to do that. We've got a carbonyl, so we've got ethanol, and we're adding HCN. Yeah, so it's going to be nucleophilic addition. So that's really good. So when we add HCN to this molecule, what do you guys think is going to be the product? If you could give me the structural formula for compound E of what you guys think it is. I'll give you guys a couple seconds to do that. Yeah, it's going to be hydroxynitrile, but can anyone give me the specific one that's going to be formed in this reaction from ethanol? Okay, all your answers are coming in. Okay, well done, guys. You guys are getting this. Okay, and then for part yeah, her name hydroxynitrile is hard. I'll go through it in a second how I would approach naming it. So, and then for part I, it's a more quote unquote challenging question, but it is worth 1 mark, so it's fine if you find these suggest questions challenging because they're supposed to be. Can anybody think of a reagent that would be used to convert hydroxynitrile into a carboxylic acid? Aisha, no, it would not be sorry, the chat's moving. It would not be nucleophilic addition elimination, as that's typically involving acyl chlorides, but this is a carbonyl, so it's an aldehyde, and we're adding HN, and that would always be just be nucleophilic addition. Okay. Lots of people are saying acid. Do you guys think that by converting hydroxynitrile into carboxylic acid, we're reducing it? Because NaBH4 is a reducing agent. So do you think that it's a reduction reaction? No, don't worry, that's fine. Aisha, don't worry about it. These mechanisms, they all sound look the same. So it's easy to conflate them, I think. So yeah, the people, I think the chat has generally got the gist of that, and that would be that it's kind of going to be involving H plus and water. So I'll just show the answer now to that and how I've drawn it. So first I identified what mechanism it was, and I know that it's nucleophilic addition, and they're going to just add the nitrile group onto this. And someone said, how would you name this? So we're going to start from the one that has the nitrile, and we count from there. So we're going to go up, and then there's there's a second carbon, and then we're going to move to the left, and there's a third carbon. So it's going to be propane nitrile, and then the OH group is on the second carbon atom, so it's going to be 2-hydroxy propane nitrile. If that makes sense to you guys. Can you explain why it's addition? I think it's just because we're adding the functional group onto the molecule. We're not actually exchanging anything and substituting things around. So substituting, kind of swapping one thing out for another, but we're actually adding on a new functional group on. And yes, they still could ask a question similar to this, as this is more of an application question. Yeah, you can say H2SO4, that would be accepted too, because it's just an example of an acid. And you also would put water too. That would be accepted too. What's the mechanism for step 2? I don't think that you need to know what the mechanism would be for step 2. It's more just an application question to see how your kind of like brain is going to process and apply this to a random molecule that you've not seen before. Could you go for the mechanism? And yeah, exactly. I think it would be the hydrolysis reaction. And for the mechanism, I went through, and this was worth 2 marks in total. No, don't say heat because it just said a reagent, not a condition. So just leave that. And this is worth 2. As I said, it was worth 2 marks. And for the mechanism from the intermediate lactic acid, I don't think that you particularly need to know that for A level. It's just more of an application question because I feel like if you were supposed to know it, they would require you to draw it. And yeah, step 2, you could write H2O as one of the reagents. This is quite a complicated application question. Yeah, sure. We'll move on. I think. Is that okay? Yeah. Okay, sure. And then this was the mark scheme and what they wanted from you. What was question? And with suggest questions, like they're usually worth like 1 mark, so don't worry too much about them. It's fine to lose those marks, I guess. But obviously you don't want to, but just practice, I think. And I think the water would just help. I think the water would remove the nitrogen from the group and then allow it to form the carboxylic acid. Um, yeah, page 4 is right. Why did it go from C1O to COH? So yesterday I went through the mechanism for nucleophilic addition, and when I went through that yesterday in the recording, this is always the mechanism. So whenever you add like some form of nitrile to a carbonyl, so either an aldehyde or a ketone, you're always going to form hydroxynitrile, and it's usually done in acidic conditions, and that's what converts it into the alcohol group, because the oxygen with the double bond O loses the lone pair from that is donated to the H plus, and then it forms an OH. Um, CN would be nucleophilic because it has a lone pair of electrons that's attracted to the delta positive H. Sorry, delta positive carbon in the carbonyl bond. Um, but yeah, and for the mechanism receptor, you don't need to know the mechanism. They haven't asked that, and I don't think they would, because you're going from a carboxylic nitrogen to a carboxylic acid, which isn't a possible mechanism. I don't think. Or at least you need to know for A level. And no, you don't need to know the mechanism, I don't think. But yeah, we'll just move on to the next question now. So this is kind of just, again, this is the continuation of the same question. And we'll just keep going. So does anybody know what these bond angles are or have an idea? Just put in the chat what you guys think bond angle A, bond angle B, and bond angle C are, and then we'll go through it. Okay, I've seen a few for A now. What about for B and C? Yeah, you don't need to know from nitrile to carboxylic acid. From hydroxynitrile from a ketone or aldehyde, you do need to know the mechanism for that. For those of you that have put 90, can you explain potentially to me why you think that is 90? I know that it looks like a 90-degree angle, but it's not. Okay. Yeah, this is shapes and molecules from physical chemistry, and they've kind of like decided to bring this into organic. So just shows how they can kind of like interlink the topics together. So yeah, for bond angle A is going to be 109.5 because it's tetrahedral, because the central carbon atom has and this could be an AQA question, Margot. So yeah. But this is an OCR question, but I thought it was still relevant because this is an overlap with AQA. And yes, this question is supposed to be hard. So don't worry if it's challenging. That's why we're here to kind of go through it and practice going through these difficult questions. So for bond angle A, it's going to be 104.5. I mean 109.5, sorry, because it's tetrahedral, as someone said. The central carbon atom, the first carbon, has like 4 groups attached to it. So and there's no lone pair, so it's going to be 109.5. For bond angle B, it's going to be 104.5 because the lone pair the oxygen will have 2 lone pairs of electrons and there's 2 bonding pairs, and that's kind of a bent bond angle. So thinking of like molecules such as water, so that one will be 104.5. And then for C, you can kind of clearly see that it's a trigonal planar molecule, and that has 120-degree bond angle because it's got 3 bonding pairs and no lone pairs. Why is B not linear? Because linear would mean that there would be 2 bonding pairs and no lone pairs. But on the oxygen, there's going to be 2 lone pairs on the oxygen. And tetrahedral will always be 109.5. And for A, Hayden, I think, who asked that, actually if it looks like 90-degree angle, and it's trying to trick you, but if you can see the carbon atom that is near A, it has 4 groups attached to it, and there's going to be no lone pairs because it's got every carbon atom can form 4 bonding pairs, and it's satisfied all of those. It's attached to 3 hydrogens and then the other carbon atom next to it. So it's going to have no lone pairs and 4 bonding pairs, which will be tetrahedral. And yeah, the shape for B is bent. And does a double bond affect the bond angle, no, it will still be for double bonds or alkenes, it will be 120 degrees. It's planar as well. Does this question make sense to you guys? It is quite a hard one, but I just thought it'd be really important to go through this so you guys can practice your physical chem. Make sense? Cool. Any more questions before I move on? Yeah. So if there's like four bonds and one double bond, so if there were four bonds and a double bond, that wouldn't be possible. Always remember, guys, this is like a core knowledge, especially when they ask you to draw molecules. A carbon atom can only form four covalent bonds at once. It can't form five. So if there was a four bond and a double bond, that would therefore be a total of five, and that would be actually it would even be six. So it can't do that. So that wouldn't be wrong. So just make sure that you memorize that you can always form every carbon atom can only form four covalent bonds. But yeah. So the answer would be tetrahedral. So it would be 109.5, 104.5, and 120. So this one is quite a challenging one. But I feel like now that I've explained it, hopefully it's more accessible and easy for you. And by the way, guys, these are like really hard questions, and typically questions be more accessible than this. But I thought it would be good to go through more really challenging ones, so then you guys can get good at these, and hopefully I'll smash them when similar questions like this come up in the exam. But we'll carry on. Yeah. So this was a 2-marker. And as you can see, guys, these kind of charge application questions, they aren't really high stake questions. This is only 2 marks out of, for example, in AQA, it'll be out of 105. So like, don't worry. And this is OCR. And sulfur can form 6 bond, but this is particularly regarding carbon. But this question could easily come up in AQA as well. So don't think that just because it's an OCR question, it can't come up in AQA, because the question could easily come up, which is why I chose it, because it's quite a good crossover question. It was 90 for 100. Yeah, the great bonds are kind of crazy. But yeah, we'll keep going. So now we have another weird mechanism question that's kind of a random molecule. Can anyone tell me what in step 1, what type of molecule is the first one? So this molecule in the top left, what molecule is this? What type of molecule is this? Yeah, well done, guys. It's an ester. Well done. Wait, what is happening? Okay, fine. Okay, so when I'm looking for, I'm like, wow, this is kind of insane. Like, I've never seen this ester before, and he's asking me to do all these crazy things. But we're going to break it down and we're going to work through it. So the first step when answering this question is that basically I'm going to highlight all the key information of what the question wants me to do. And I'm essentially going to split the question into 2 parts in my head, an A half and a B half. So firstly, it says to add the relevant dipoles and curly arrows to show how the intermediate is formed in step 1 of the mechanism. So the first task is to add the relevant dipoles, and also then to add the relevant curly arrows for step 1. I'm going to take it one step at a time. So with dipoles, that would imply that there's kind of like an electronegativity difference. So that would mean that there would have to be some form of polar bond within the molecule. Can anybody see any polar bonds within the molecule that we could add a dipole to? Just put it in the chat for me. Yeah, as everyone said, the C double bond O. And can anyone tell me which one would be the delta positive and which one would be the delta negative? Yeah, the carbon is going to be positive and the oxygen is going to be delta negative. Well done, guys. See, we break it down and we're making it more digestible. Okay, so now I'm thinking about this question, I need to think what is happening between step 1 and step 2 that what has changed in the molecule. So can anyone tell me what has changed from during step 1? What has changed in the molecule? Just put in the chat. Yeah, the double bond breaks and there's now an O double bond O. So that implies that the bond has been broken. So how are we going to break that double bond between the molecule? Where's the arrow going to go? The first arrow going to go? Yeah, as someone said, yeah, it's going to go towards the oxygen. Yeah, yeah, well done. Okay, so we've already got basically 2 marks, I think. So we've added the dipoles and now we've drawn 1 curly arrow. So that's like 1/3 of our job for this part done. But we're gonna transfer electrons to the double bond to the oxygen from a double bond. But then we've also got this kind of nucleophile, the hydroxide ion. And what's that going to be attracted to? Can you guys put in the chat for me? What the OH ion is going to be attracted to? Yeah, it's going to be attracted to the delta positive carbon. So what do we need to do? Yeah, we need to draw a curly arrow from the oxygen to the carbon. from the lone pair to the carbon. So yeah, that's part of our job done. Well done, guys. So see, we're just kind of breaking it down into digestible steps. And by the way, this is actually wrong. By the way, the two dots should be on the right hand side. So it should be near the oxygen and going towards the carbon. So that's wrong, by the way, guys. Sorry about that. Just to clarify. So that this should actually be marked wrong. Make sure that the arrow can come from a negative sign, or in the mark scheme, it does say you can also add a lone pair and draw the arrow from that. But make sure that it's near the oxygen, not the hydrogen. That would actually be wrong. Yeah. No, you wouldn't be marked down if you wouldn't draw the dots. You can draw it from the negative charge too. So there we've done quote unquote part A. So now we need to move on to part B. So what has changed during step 2? What has changed in the molecule? And this will count as base hydrolysis as well, Zach. So well done for noticing that. So what's changed between the intermediate that's formed and step 2? Yeah. No, the arrow must be curvy. Yeah, the OCH3 has been chopped off and the double bond has been reformed. Well done, guys. So when you're answering these kind of random, kind of unfamiliar, novel mechanism questions, just think about what's changing in each step and how the arrows that you're drawing are going to like cause those changes. So how are we going to reform a double bond? Where is the arrow going to go? Yeah, arrow from lone pair to bond, from O to bond. Yep. Well done, guys. This is really good. You guys are doing great. This is a really hard question, so well done, guys. So yeah, that's our first arrow. But then we also see how the OCH3 is been chopped off. So how are we going to show the chopping off of that through the use of arrows? Where's the arrow going to go? Towards arrow from CO bond to oxygen. Yes. Well done, guys. This is amazing. Okay. So this is where the arrows would go. As we can see, the carbon oxygen double bond has been reformed and the OCH3 has been chopped off. So we just need to show that in an arrow form. Yeah, I'm sorry, through the use of arrows. So yeah, well done, guys. See, so this question wasn't that bad. So this would be how I would draw this and how I would approach this. And yeah, I think this is an example of nucleophilic addition elimination, but it's just in a more novel and new context that you might not have ever seen it in before. No, we don't. For step 2, we don't need to, as it didn't tell us to in the question. So don't worry about that. It just said to add the curly arrow. So make sure that you guys just read the question and don't, because I feel like sometimes if you kind of like go above and beyond and do things that the question doesn't want you to, and then if you get it wrong, they can actually mark you down. So just be careful of that. Why would the intermediate be needed for this question? I don't think the intermediate the intermediate is needed actually, because you need to like again reform the double bond and then chop off the CH3, and that can only be done through a secondary step. You can't do that all in one step. Like you can't just go from the first product to the end through the use of one arrow. So you need to have an intermediate molecule. Can you remind me why the arrow is going from C to O in step 2? No, it's just because the electron pair is basically being redonated back to the carbon oxygen bond to form that double pi bond again. Nicole, that makes sense. Does this question make more sense to you guys now? So when you see these questions, guys, don't freak out. Don't freak out. They're not as scary as they seem. Just you guys know your mechanisms. You know what the arrows mean. You know what they're used for. And what does the bottom arrow represent on step 2? It represents the breakage. It represents the breakage. So the electrons from the C double bond, the CO bond are being transferred to the oxygen. So then the bond breaks. Yeah, you just need to kick out the OCH3 group. I think I just explained that, Nicole, but I can go over it again. Does this make sense to you guys? Any more questions or ready to move on? Just put a yes, so you're ready to move on to the next question. Yeah, and yeah, I think it could form a salt with sodium if it was sodium hydroxide was the reagent that was used, but we don't know. So but yeah, so well done, guys. This is what the mark scheme says, and yeah, we've got all of our marks. So well done, guys. You guys did great on that one. I'll leave this on for a sec just so you guys can like read that. I guess it's also important to read because, as I said, I made the mistake of the curly arrow must come from the low pair and the oxygen, and it must not come from the from the H. And also, as someone asked, you can still get the mark if you draw it from a negative charge on the oxygen. And the curly arrow must come from the lone pair on the oxygen. And again, the same point applies. But yeah, we'll carry on. Okay, again, now we have another crazy or more difficult question, but we're going to just break it down again. So my first step is just to highlight all the key information of the question. So it says this question is about phenols, is about the reaction of phenol. And honestly, yes, I feel like at a certain point, towards the end, when it gets close to A levels, you can do the questions from different examples. And the reason why I chose these questions is because they are really, really hard. And AQA could do questions like this, and they have done some evil ones before. So just practice as much as you can, because chemistry is chemistry at the end of the day. So it will never really change. But yeah, as I said, it says this question is about the reactions of phenol. It says salicylic acid can be prepared from phenol as shown below. And as I said, when we do these random organic synthesis questions, I've never really heard of salicylic acid before, but I don't really care when I'm doing the exam. I'm going to just try and focus on what I do know. So I'm going to look at what's changing. So as we can see during stage one, the OH is kind of kicked off to form an O minus. And then we can see how there's a carboxyl group added, and then it gets converted back into the phenol group and the alcohol group and the carboxylic acid. So the question says to complete the mechanism below for stage one and stage two. And there's basically, again, essentially, again, I'm trying to break up the question into like kind of manageable parts. So it says, first, you need to show the curly arrows, structure of the intermediate, and the missing formula on the dotted lines. After stage two, I'm kind of lost. Okay, it's fine. We'll go through it now. And salicylic acid isn't used in the creation of aspirin. But yeah, when it comes to these like application questions, guys, don't worry about what the molecule exactly is. Just think about, you need to think, I know my mechanisms. I know every mechanism that's covered in the A-level specification. So I need to think, although this is a random molecule that I've not really heard of before, I need to think, how can I kind of apply my knowledge of mechanisms to this novel or random context? And these questions could come up in AQA too. So make sure you're listening, because I feel like these questions still can come up as well. In AQA, they have done some questions like this before, especially in, I think, my paper, so 2023, there were some like weird mechanism questions, I think, where they were kind of like half done for you. But yeah, we'll actually get started on this question now. But yeah, that's how I approach the question, just making sure firstly to see how the molecule is changing. And so far, these questions have been OCR, but I thought that they were good questions because they're quite interchangeable, and AQA could easily do a question like this as well. So we're going to talk about stage one now. So can anyone tell me what's changing during stage one? Yeah, it's losing the H. Elimination, H removed. Yeah. And as people are pointing on, you're making water. So we're going to add water onto the dotted line as a product. So how are we going to show that the H is lost? How many arrows do we need to draw, and where do you guys think they need to go from? Basically draw an arrow from lone pair of oxygen to hydrogen to the H and then to the O. From lone pair to H, arrow from lone pair to H, and from bond to O. Yeah, well done, guys. And we're forming water because, I think it kind of makes sense. The OH is attacking the hydrogen, and then we've got two hydrogens and an oxygen, which is going to make water, which is a neutral molecule. So that's why water is formed. And as you guys can see, these are how our arrows are going to look. And as I showed, the difference between it is that bond is broken, and we do form water. Does that make sense to you guys? So when these random mechanism questions comes up, don't be scared by them. They're actually not too bad. I hope I've made them seem a little bit better. So don't freak out, just keep calm and look at how the molecule is changing between the different stages and steps. Okay. Yeah, the water molecule is being formed through the removal of the hydrogen. Ramisa, could you potentially rephrase that? By the other way around, what do you mean? Because why doesn't the arrow go to the oxygen? It is, but I just can't draw well at all. I'm not very artsy, but just pretend that it's slightly more to the right and he's actually going towards the oxygen it's supposed to, but I think this will still be acceptable anyway. But yeah. Okay, ready to move on, I think. I think this is fine. Okay, so next we need to think about, so go back to this part now. So now I'm going to be thinking what is changing from between stage two and stage three, and what type of mechanism is this going to be now? Do you guys think, or what mechanism do you think this is an application of? I'm just putting in the chat. Yeah. Hassan, just be careful. It's not nucleophilic substitution, it will actually be electrophilic substitution, as you guys have said. So well done. So yeah, just identify what mechanism this is. It's kind of like a weird example. So how do you know? Okay, you know because essentially the only mechanism that you learn at A level that involves benzene is electrophilic substitution. Um, and we're adding something onto the ring. So, for example, such as we would do in nitration, but it's kind of like a new context. So rather than adding an NO2 group or adding an acyl chloride group, we're adding a carboxylate ion, sorry, to the benzene ring. So whenever you add a functional group to a benzene ring, I think that's always going to be electrolytic substitution. Um, yeah, yeah, facts, Aura, facts. Yeah. Well done, guys. You guys are really smart. Literally better than me when I was in year 13. Um, okay, so where do you guys think the arrow is going to go? So where do you think that the arrow so we need to draw essentially need to draw I'll give you guys a hint. We're gonna need to draw two arrows. So where do you think they're gonna go? Okay, benzene ring to the carbon. And yeah, for the benzene, typically it's gonna be electrophilic substitution. From benzene ring to delta positive C. Okay, Sarah, I think in oh yeah, that's no, that's right, that's still right, fine. Um yeah, ring to carbon, arrow from benzene ring. Cool, Izzy. Okay, yeah. So that's gonna be one of our arrows. And then also, as Hassan has said, from the double bond to the oxygen. Hassan, can you tell us why you think that is going from the double bond to the oxygen? Because that is correct, but why do you think that? Is it from the carbon to the, it's always from the deglocalized ring to the carbon. And that's something I always used to get mixed up as well. So yeah, just check over your mechanisms, guys. I feel like sometimes it's easy to kind of like go into autopilot mode. Yeah, and it is going to form an O minus as a product. Yeah, well done. Cool. Is it just inducing a dipole in the CO2? Yeah, I think it would do that. Yeah. Um, why is it COO negative? Because it's a carboxylate ion. For example, if it was COO Na, that would have the COO minus negative and also Na plus, so the charges cancel out. Or if it was carboxylic acid, it would have COO negative and then H plus, which would cancel out the charge. But because it's just on its own, it's going to have a negative charge. But yeah, as Hassan said, we've kind of got a new electrophilic substitution, and we need to break that bond and form O negative as a byproduct of that. And we've kind of got a new electrophilic substitution that we've not seen before, but we're not going to get scared because we're good A-level chemists and we're going to aim for that A star. So yeah. Okay, so now we need to think about the intermediate. Can anybody think about what the intermediate? Yeah, okay, and I'm straight on it. Horseshoe and add extra H bond in intermediate, correct. Okay, did anybody remember, if you were here yesterday, what I said about the horseshoe and how it needs to look? Will it always be like this? When making an electrophile, if there are, yeah, it has to cover three or more carbons, has to be where the O negative is bonded. Will it always be like this when making an electrophile if there are double bonds? Yes, I think so. It needs a plus sign and should be more than half. Cool. Okay, so I'll show you guys how my intermediate looked. I can't draw benzene, just to give you guys a disclaimer, but you guys should be better than me at drawing it. But I still was fine in my level, so don't worry. Oh wait, I can't say sorry. This is how my intermediate looked. Do you guys think this is good, bad? Let me know what you think. Good. I tried to practice after you guys cussed me out last time. But um ugly but gets the mark. Sure. Yeah. And then after we need to draw the double bond to the positive broken horseshoe ring, and then we're going to form H plus as our byproduct. This might overrun again, sorry guys, but if you guys need to leave, the mark will still I mean, the recording will still be up, so it's fine, but I'll just keep going anyway. Do you lose the mark? Yes, you would lose the mark, and don't give the examiners excuses to lose your marks. So yeah, just try and make sure it's as good as possible. But I was still fine in my A levels, so don't worry. Could you please explain the products of the intermediate? Sure. So when the double bond goes from the hydrogen to the wait wait one sec. I need to scroll. Um, can can you please explain the products of the intermediate? Like why it forms COO minus. I think that's just because that's what adding onto the um we're adding onto the that's like the functional group that we're adding onto the benzene ring. So that's why it's gonna form that. Um I'm not really sure how else to explain it, but does everything else make sense to you guys? It's kind of just an application of electrophilic substitution. Um how do you know which position? Sorry, so the horseshoe always faces the complex, so with the H and then the functional group that you're adding, that's always the way it faces. Um, and the benzene will attack the COO. It's because the electrophilic ring of electrons, I think, would repel the electrons within the carbon dioxide molecule, and it will cause it to induce a dipole and cause it to be cause it to become electrophilic. So that's why. And yeah, the indication is because that's the only way that benzene can react through electrolyte substitution. It doesn't undergo substitution. I mean, it doesn't undergo addition reactions. It can't because it just requires way too much energy. It's not energetically favorable to do that. Um, but yeah, any more questions or ready to move on? These questions are all OCR, but like this could easily come up in AQA in a paper 3 or even in paper 2 at the end, like it's kind of like a last hard question. But yeah, I hope this question makes more sense to you guys now. It is quite a hard one, but we've gone through it now, so hopefully it makes more sense. But I'll just move on. And this is the mark scheme for this part of the question. And yeah, they're really strict about the ring, so don't give them excuses to make you lose marks. But yeah, okay, we'll keep going. Okay, this is an AQA question now. So it says 1,4-diaminobenzene is an important intermediate in the production of polymers such as Kevlar and also polyurethanes used in making foam settings. That is just waffle. I'm going to ignore that. So I'll just keep going. As a possible synthesis of 1,4-diaminobenzene from phenylamine is shown in the following figure. So we've got all these steps. And it says a suitable reagent for step 1 is CH3COCl. Ethanol chloride. Name and draw a mechanism for the reaction in step 1. So what mechanism do you guys think this is going to be? Yeah, nucleophilic addition elimination. Got it. So there's already one mark. I accidentally removed the slides for this, but I'll add it at the end. But I did add slides where I drew the mechanism, but I've not got them anymore. I am not sure what happened there, but it is nucleophilic addition elimination. And I'll add them at the end and send the PowerPoints to each other. I am not sure what happened, but sure. Maybe it's at the end. I'll check. But we'll just keep going. I don't know what happened there. Okay. Again, another benzene question. Sorry about that. Hopefully you guys, I feel like you guys know how to draw that mechanism. Just keep practicing. And I went through how to draw it yesterday, so hopefully you guys are experts now. But we'll keep going. It says, a student investigates the relative ease of nitration of phenol, benzene, and benzoic acid. The student finds the conditions, and it shows them. The student finds that the conditions required for the nitration of each compound are different, as shown in table 17.1. So we can see how phenol, benzene, and benzoic acid require different conditions. And it says, state the trend in the relative ease of nitration of phenol, benzene, and benzoic acid. So guys, in the chat, how would you guys answer this question? And just put what you would write for this. But I have now gone into overrunning time, but I'll try and keep on track. So relative ease, just they're kind of like just waffling, but it basically just means like how easy is it for the reaction to occur. And as you can see, the temperatures are going up. You're starting to require catalysts. You're starting to require more concentrated versions of the product as opposed to dilute. So that's kind of how I would approach this question. Yeah, okay, cool. So yeah, phenol is the most easily nitrated and benzoic acid is the least easily nitrated. And also I'll go back, and that's because it just requires high temperatures, more concentrated versions of the nitric acid and then H2SO4. Does that make sense to you guys? Cool. This is a nice one marker, I think, just to warm you up into the question. Okay. Now they've now gone and turned this into an application question. So it says, apply your knowledge of the bonding in A rings to explain the trend shown in BI. So firstly, we'll just go through the type of bonding that occurs in benzene. So here we'll go through it. So benzene has a structure of C6H6. Isn't it possible to answer? Yeah. Yes, you didn't need to know arenes. An arene is just a molecule that contains a delocalized ring of electrons. So it contains a benzene ring, essentially, Emma. So that's what an arene is. It's also the same as an arene and aromatic can be used interchangeably. It means the same thing. So don't, but yeah. So benzene has C6H6 as its formula. And yes, you need to know about calculate for that. And it has 6 carbon atoms in a hexagonal ring with one H atom bonded to each. IMF is intermolecular forces. With one H atom bonded to each carbon atom. Each carbon atom is bonded to 2 other carbon atoms and one H atom by single covalent sigma bonds. And that means there's one spare unused electron in each carbon in the p orbital, which is perpendicular to the plane of the ring. And that is basically the same as that of alkenes. You've got that the carbon atom is only using 3 of its bonding pairs to form sigma bonds, and then you've got one spare electron in the p orbital that overlaps to form pi bonds. And the 6p electrons are delocalized in a ring structure above and below the plane of carbon atoms. And this is a planar structure with a bond angle of 120 degrees. And there's an equal bond length between the single and double bonds. These are just some facts about benzene. I think I have seen this as a potential 6 marker before. We were just asking you to describe the structure and bonding of benzene. So this is just something to, again, memorize, try to understand it, make it into flashcards. But does this make sense? Any questions about this? Okay, I'm gonna just move on because I can't see anything. Cool. Okay, so we're gonna go back. She says apply. Now we know the bonding in arenes or molecules that have benzene rings. So we need to go back and think about how the addition of a phenol group or addition of a carboxylic acid group is going to affect their ability to be nitrated. And I saw someone already. Nicole's that she got it. She's on it. But we'll go through it now. So this is the kind of table that I made with the answer to this question. So with phenol, it has a very high susceptibility to attack because, as Nicole mentioned, a lone pair of electrons on the oxygen delocalize onto the ring and they again join in onto the benzene's delocalized electron ring in the middle. And that increases the electron density, so it's more likely to attract the electrophiles. Whereas with benzoic acid, the carboxylic acid group is going to remove electrons, it's going to decrease the electron density within that ring of electrons in the middle. So it's going to be less likely to attract the electrophiles, which is why the conditions are much more rigorous and why you need the catalyst and the high temperature and the concentrated nitric acid. So that's kind of the answer to this. This sometimes comes up, but again, just something that I wanted to go over again because someone asked me to go through like withdrawing groups and kind of electron density. But I hope that makes sense. Does anybody have any questions about this? Any questions? Just put in the chat. I'll be happy to answer. Everyone happy? Okay. So with electron withdrawing, so all of the kind of electron, like within benzene, it's got that kind of localized ring of electrons within the middle, and the carboxylic acid group is going to basically take the electrons from that ring, and then take them away and add it to itself to make it that CO, the carboxylic acid group stronger. And Aisha, this is very difficult. These are very complicated concepts. So don't worry if it's hard to understand. I'll try to explain again for you guys. So, okay, so with phenol, as we know, in the oxygen, in the alcohol group, it's going to have a lone pair of electrons, right? It's going to have 2 lone pairs of electrons. Does that make sense? That it has two lone pairs of electrons. Yeah, cool. Okay. And we'll go through Amy in a second. So that has a localized ring of electrons, a lone pair of electrons. And then in the middle, then we've got a localized ring of electrons. Those lone pairs are going to be attracted to that ring of electrons in the middle. The lone pairs on the oxygen are going to be attracted to those rings of electrons in the middle, which basically increases the number of electrons that are contained within that localized ring. So it's going to be more likely to attract electrophiles and more likely to be attacked and nitrated. Does that make sense? And this could come up in AQA as well. But now you know about it, so it's good. But these are complex concepts. I'll try and explain one more time. So you've got a localized ring of electrons in the middle of the benzene ring. The lone pair of electrons on the oxygen are going to be attracted and donate that to that ring, which is going to increase the number of electrons that are contained within that area. Therefore, it's going to be more likely to be attracted to the more likely to be attracted to the um more likely to be attracted to the electrophiles that are going to attack the benzene ring. Whereas with the carboxylic acid group, it's going to remove electrons from that ring as opposed to adding them like the oxygen does. And with the amine, that also has a lone pair of electrons on it. So that would also have a high susceptibility to attack as well. Does that make sense? Guys, don't argue. It's not like don't. It's not that deep. But I don't know what's happening. But just like chill. Yeah, you can say positive inductive effect. As well. Uh, yeah. So this is kind of the explanation. And then yeah, sorry, I meant to answer that. So is the OH or benzene? So in this case, the benzene will class as the electron withdrawing group because it's removing the electrons from the oxygen group. And yeah, electrophile is. Um, can you explain why ammonia is a stronger base than phenyl amine? Again, it's the same reason. The lone pair of electrons on the nitrogen atom are going to be donated into the delocalized ring. So it's gonna decrease the electron density of the nitrogen. So it's gonna be less likely to be like donated to H plus ions. So it's gonna less likely to act as a base. Whereas ammonia, it's sorry, I'm just reading the chat. Whereas ammonia, it's gonna be like ammonia, there's nothing to like donate the electrons to. There's no other electrons in that area. That's kind of the end of this. I don't know if you guys have any general questions about A levels. I can stay around for like 5 more minutes. If you guys just put any questions you have about like A levels or like revision or anything, or like anything you want to know, yeah, you get it. That's great. I'm happy that you get it now. But if you guys have any questions about like A levels, anything like that, just put in the chat. And sadly, I wasn't gonna be. I couldn't find any AQA questions because they were quite long. But if potentially I might do more classes in the future, so I could potentially go through more AQA questions then as well. But I'll send some exam questions to the group chat for organic. I'll just go through the chat. For my A levels, I did AQA biology, AQA chemistry, and then Edexcel math, and I got 3 stars in that. Yeah. So when I did my A levels, biology paper one was like low. Biology paper one was really bad. And I was like, wow, that was awful. But just I feel like if you have one paper that goes bad, just think you have all like loads of other papers. So just try and have like a redemption arc and try to like do as well as you can in those ones. And yeah, I'll try and go through the questions faster next time. But last time I was going, yeah, apparently yesterday I was going too fast. So like I tried to slow down more this time. With regards to the command words, I'll send to the chat. AQA made like a list of like what the command words mean. But for example, describe is to kind of just say what you can see, whereas explain requires more detailed understanding. So you need to like give the reasons why. And with ChemRevise is a really good resource for chemistry. I use that. For the AQA biology essay, I just practice writing essays. I remember I always used to use phytochrome C as like my out of essay topic. So just learn one out of essay topic that links to like those topics and then just do that. But mine was phytochrome C. NMR is really hard. Just watch loads of YouTube videos. So between exams, I would just like do in order of priority of like what exam I had next. So if I had, example, say if I had chemistry paper one on one day and then 2 days after I had math paper three, I'm not going to start revising math paper two. I'm not going to start revising, for example, I'm not going to start revising biology. And now, guys, it's time to just do exam questions. I think NMR was covered in the previous session, and there will be more sessions in the future. I can probably come back and do some more. And yeah, anaerobic chemistry is good, and just through NMR, just keep the exam questions to practice that. I'm glad you guys enjoyed the class. For practicals, just understand why like why each step is done. So like know why it's done. I think I use physics and math tutor as my for my practicals. Just learn why each step is done and like the safety protocols behind it and why what reagents you're using and why. How was transitioning to med school? The transition to med school was good. I go to Imperial College London right now. It's really good. It's fun. The work's kind of hard. We do get pushed a lot, but it's really fun. And what we learn is really interesting. So good luck if there's any medics that are going about to go into med school. London's great. I'm not from London, but it's really fun being here, like exploring what it's like to live in being living in London, going to all the stuff. But yeah, I'll just I don't know when its A level start, but I think they might start on 4th of June or something. I think someone said that to me. So I just focus on my paper ones and paper twos. I'll try and find some notes for bio, but I think I might have like written them all up because I was like excited that they were done. Yeah, just do all these exam questions, do the past papers under time conditions now. And website searches, Physics and Math Tutor, Chem Revise for chemistry, AQA Science School with a S is really good as well. SKOOL Science School. That's really good too. For math, Nika Maths, Mad as Math, if you want to aim for an A star, and just doing past papers. And you can also do other exam board questions too. Um, but yeah, I'll probably end the meeting now if there's any more questions. For bio AQA essay, for the importance bit, what did you talk about? Um, I usually just used to do like AQ, used to do like respiration, just say, or like oxygen to terminal, electron acceptor, stuff like that. Um, but yeah, just kind of like low-key waffle. I don't know. That's what I did. It kind of worked out, I guess. I thought this was helpful. You guys can all like go now. I'll just stay around and see if there's any more questions. Thanks for coming, everyone. For memorizing synthesis maps H, just keep drawing them out over and over again. Um, maybe start off small, just like build it slowly. So draw like, for example, like half of the map one day, then draw that same half again the next day, then add on another bit, another bit. But yeah, I'll just answer the last few questions if there's any more. For bio, I just used Bride with Olivia and Physics Math Tutor, and then just past papers. They were quite good. For me, at least. The CGP questions are quite good as well, too. Um, yeah, that seems to be it. So I'll just stop sharing and end the meeting now. But thanks for coming. Thanks for coming. It was good to have you all here. Um, with math, just use Mad as Math and use Nika Maths and just keep practicing some questions. Math is kind of easy, I think, once you just practice loads and loads of questions, you get really good at it. But yeah, thanks for coming. I'm gonna end this now. Um, use Mad as Math to find modeling and harder questions. Mad as Maths, and yeah, some of them are insanely demonic, but just still do them anyway. Because you're good at problem solving for it anyway. But yeah, that's it. Thanks for coming, guys. See you guys soon, hopefully. Or we'll just end this now.